All right. Hi. So we are back. I'm still muted. Hello, hello, hello. I think it's okay. All right. So hopefully I can hear myself. Hello, hello, hello. All right, cool. So this is 1.3 continuity and behavior and limits. The objective is that you'll be able to use limits to determine the continuity of a function. So continuity is just the how continuous it is, basically, whether it's continuous or discontinuous. All right, not continuous. All right, whether there's any breaks or holes or gaps or anything. So in order to do that, we need to talk about limits, and limits is something that you're gonna see quite a bit. Okay, so you're gonna see the form. Let's see, you can see down here. The way you read that is the limit of f of x as x approaches c. Okay, so one more time. The limit of f of x as x approaches c. So on the graph um, over here, like say uh, 7, but 4. All right. So here, so around 4, it's around 1, right? The y. So the limit of f of x as x approaches 4 is about 1. Okay. And we'll talk more about that later. Um, yeah, if the value of f of x approaches a unique value L as x approaches c from each side, then the limit of f of x as x approaches c is L. Oh, okay. So here, as you approach it from the left, and as you approach it from the right, it's approaching L, that y. So you're looking for that y value. Okay. All right. Hopefully that's clear. If not, we'll go over it again. Don't worry. Oh, wait. I should put that on the notes. Let's put it on the notes. Sorry, I had to make some calls to parents, so I'm a little late. So the video might be short. Might be a good thing. All right. So we have 4 different possibilities. All right. Either it's going to be continuous. Continuous means that the graph just is goes on forever. Okay. There's no stops, no breaks or anything. It's all connected. Now here's 3 different types of discontinuity. Discontinuity is where the graph is broken up basically. So you have an infinite discontinuity. Infinite discontinuity is whereas you approach it from the left side, and as you approach it from the right side, all right, it, it either decreases indefinitely or also increases indefinitely. Okay, so this is you'll probably know from algebra 2 it's like an asymptote. Okay, it's an invisible line that the graph approaches but never touches. So that's an infinite discontinuity. And then a jump is where you're basically jumping. So you imagine here, la 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 la, jump, and then jump all the way up here. Okay, so that's a jump discontinuity. Okay, so when you're approaching it from the left and the right, they're two different numbers. Okay, so you get two different values. You'll see that when we look at examples. And then the removable discontinuity, this is also known as a hole, okay, in some books. This hole is where when you approach it from the left and you approach it from the right, okay, it's going to be the same value. However, when you plug in that point, it doesn't exist. Okay, so it's like just missing. It's gone. Who knows what happened to it? All right, so here's the different. Oh, and we'll talk about the limits. Let's take a picture of that first. Picture time. Oops. Picture time. All right. So it says here, notice that for graphs of functions with a removable discontinuity, the limit of f of x at point C exists, but either the value of the function at C is undefined, or as with the graph shown, the value of f of C is not the same value as the values of the limit at point C. Okay, so when you plug it in, totally different number than what it's approaching on the left and to the right. So either it's there, but like some at a different place, or it's just not there at all, like what we saw in the last picture. I smell popcorn. All right. And the infinite and jump discontinuities are classified as non-removable discontinuities. Um, and yeah, so to do this, we need to do the continuity test. So a function f of x is continuous at x equals c if it satisfies the following conditions. So f of x is defined at c. That is when you have a function f of x, blah, 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 and then you plug in your c. And if you plug in your c, you get a number. Yay! That means it exists. Woohoo! All right. If you plug in c and you get a does not exist, you get one that's not possible, then it does not exist. I guess that's pretty self-explanatory. Popcorn smells good. Butter. All right. And f of x approaches the same values from either side of c. So you have to check two things. You have to check the limit of f of x as x approaches close to c on the left side. Okay. And limit of f of x as x approaches c on the right side. And you'll see how we do that. So the value that f of x approaches from each side of c is f of c. So if this, okay, so we need to check this, f of c exists. We need to check f of c from the left. I'll put C negative and limit f of x as x approaches C positive. Yeah, sounds okay. Okay, equals a number. This one equals a number. Okay, if they're the same number. Similar number. Okay, if they're approaching the similar number, that's the second uh, one to check. And then the third is that limit of f of x, this x approaches C, is equal to f of C. If those are the same, hey, 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 all three work out, then it's continuous. Okay, so let me show you some possibilities. Actually, there's only like three that we need to. We need to check. Alright. And I want to put a table here. I'll do it later. I'm sorry. I'm just distracted by the smell of butter. Butter popcorn. Mmm. Seems like I'm teaching in the movie theater. All right. Where's Tom Hanks? He's my favorite. All right. Let's go on. This is an example. Notice that they have three things. All right. Another example. Here they have two things. One doesn't exist. And another one. All right. So I don't know if we'll be able to get through one of these. Hopefully we can. All right. So let's do this. I'll try to do four, number four, and then I'm going to, yeah, if you want to try three, yeah, try three. Okay. I'm going to try four. And yeah, let's see where it takes me. I should probably do one first. That's okay. I'll do one later. So try number three. Okay, so number four, we're gonna do we're gonna test two things, so A and B. Okay, so I'm gonna do one first. Just do one at a time. You're gonna check to see if h of -5 exists. Okay, so here we're just gonna plug it into the equation. So we have -5 squared minus 25 over -5 plus 5. And -5 squared is 25 minus 25, but that doesn't really matter because on the bottom in the denominator we have 0. -5 plus 5 is 0. Okay, so you can't have 0 over 0. That does not exist. So right away we know it's one of the discontinuities. Okay, now we have to find out which one it is. So the way we do that is we have to check the next one. We have to check the limit. And the way we check the limit is we're going to do a table. Okay, so we're going to make a table. Table time. So we had to go to IKEA. We had to get a table, and then we have an X, and then here H of X. So it's a XY table basically. And I like to do 3 on the left and 3 on the right. Okay, so you're probably thinking, what are you talking about? So here is going to be our -5. That's the one we're going for. -5. Okay, so we want numbers that are a lot smaller or smaller than -5. Okay, so one that's really close. So this one's going to be -5.001. And then, oh, I'm sorry. It looks like on the notes I left one out. So here you can do, uh, make it a little bit. So this one is really close. And then you want it to be a little bit farther, like -5.01. And then a little bit farther, -5.1. Okay. And then over here on this side, you're going to choose numbers that are bigger. So numbers that are bigger, but one that's really close is -4.999. And then here you have -4.99. Then here -4.9. So hopefully you're seeing that pattern. 001, 0.1, 999, 999. All right. That's because this is a negative. You'll see what the positive one looks like if we have time. So I only did this one. This was -10.1. Oh, and we get this by use Desmos. Okay, so you plug these in. Okay, so you're plugging all these numbers into the function. And when you plug it in, you get -10.1, negative 10 point, I'm going to assume -10.01, and -10.001. All right. And when you plug this one in, you get -9.999. Here, I'm assuming you get -9.99, and this one, -9.9. All right, so it looks like they're approaching the same number, right? So -10.001, -9.999. So it looks like it would be -10. Okay, looks like approaching same number. All right, that means that the limit of f of x as x approaches c does exist. Okay, if they were approaching totally different numbers, like say this is approaching -10 and this one is approaching +10, they're totally different numbers, then it does not exist. But here it does. And this one, it does not exist if we plug that in. Okay. And we put the x there because it does not exist already. We tried that one. So here, we get does not exist for the first part. The second part, it exists. Okay, so here's a table. You're not going to see this table anywhere else. Why? Because I'm crazy. I'm just kidding. So this is one that I just made up myself. I think it's helpful. I like it. Okay, so here you have if the limit of f of x as x approaches c exists, and here the limit of f of x as x approaches c does not exist. And remember, does not exist means approaches different numbers. And here on the left side, we're going to have f of c exists. And here, remember that equals a number. And here, f of c does not exist. Okay, so two possibilities for each of those. And then if they both exist, then it is continuous. If the f of c exists, but the limit of f of x as x approaches c does not exist, then this excuse me, this one would be a jump discontinuity. If f of c does not exist, but the limit of f of x as x approaches c does exist, like what we have here, this is a removable discontinuity or a hole in some pre-calc books. And then the last one, if neither of them exist, this is an infinite discontinuity. This is a removable discontinuity also. Okay, so here does not exist, and here it exists, so ours is a removable discontinuity. That's discontinuity at x equals -5. All right, yeah, I'm sorry, I didn't have time to check the +5. I'll go over that tomorrow. That is it. Oh, why did I put a box around that? So I should put the box around, this is the answer, removable discontinuity. That's better. All right.